All right, crash course on carbon-13 NMR. Carbon-13 NMR is substantially easier to analyze because we don't have J coupling. Now, full disclosure, carbon-13 atoms do participate in J coupling, but because the odds of finding two carbon-13 atoms next to each other naturally is like 0.1% or less, we don't really see this effect. So take a look back at 1H NMR, and what you'll see is that I told you there are three pieces of information you get. You get the functional group, that's the chemical shift. You can get the integrated area, which is the number of hydrogens, and then you can get the number of neighboring hydrogen atoms based on the splitting pattern. Well, what makes carbon-13 so much easier to understand is we don't have J coupling. So it's just the first two pieces of information, the functional group and the number of atoms that look like that functional group. The challenge with carbon-13 is identifying what's considered a unique carbon. This is kind of a challenge with hydrogen, but not so much because it's a little bit more obvious to see. When we want to figure out the number of unique carbon positions, it's not just looking at is it a CH2 group, the question is it a CH2 group, what is it bound to? If we have a methyl group, what is it bound to? Because if we have two carbon atoms that are both methyl groups, but one's bound to a methylene versus one is bound to like a methine, those are going to give different chemical shifts. So if we look at this diagram, again, we're just going to assume that the R groups here don't contain hydrogens, and in fact, in this case, we're going to assume they don't even contain carbon. So maybe it's something like a bromide. We see three unique carbon positions. This is next to whatever this R group is. This is what's next to this R group. Now, you can sit back and say, well, this is, these R groups are the same. These carbons should have the same chemical shift, but they shouldn't. Because this one's bound to a fluorine, and this one's not. This one does not look like this, even though, well, one, it's not bound to an R group, and the second is that it's bound to a carbon that contains a fluorine. So this is kind of the really hard thing to see with carbon-13 is you have to look at what's bound to it. And if you look at a carbon and you write what's bound to it, and you look at another carbon and look at what's bound to it, if they're not the exact same thing, they're going to have different chemical shifts. But unlike carbon-13 or hydrogen where we saw a splitting pattern, we're just going to see a single peak. And because we have one carbon, and one carbon, we're going to have integrated areas 1, 1, and 1. So carbon-13 is a lot more easier to analyze. It tells you the number of unique carbon positions, basically number of unique carbon functional groups. And the way you determine that, look at the carbon atom, look what is around it. If you have two carbon atoms you think are the same, look what's around them. If it's not the same thing, they're going to have different chemical shifts.